Thanks for that intro, Marley, but then I was going to say I wrote it, so. Good morning, everybody. It's good to be with you today. And the conversations and dialogue the last couple of days have been great, and including the one this morning from Mark. And it's really been interesting to hear the diverse, viewpoints and really around the whole subject of what we're talking about. I'm from the vehicle side, so I'll give you a little bit of background on Quantum real quick. I don't have a slide on it, but we're basically a vehicle integrator. We develop powertrains, hybrid powertrains, EV powertrains. We do refueling equipment for hydrogen, et cetera. We do natural gas vehicles. We do a whole gamut of different things. For the most part, we don't design battery systems. We don't design power electronics, although we are dabbling in that in some areas. But for the most part, we bring systems together. And one of the things that we do is we develop the software and controls to make all this work together as a system. And then we do basically the systems engineering, validation, and put the vehicles out there. So we're basically a low-volume manufacturer, if you will. And I tell you that only so that you understand the perspective I'm coming from when I go through some of these slides. So Marley had asked me to go through several topics, and they're kind of diverse, and I got to go through them quickly because I probably have too many slides. It was 3 hours. I cut it down to 2, so bear with me. Understanding key characteristics of new battery technology. We'll talk about that a little bit, but we've been talking about that the whole conference, so I'm going to go through that fairly quickly. Utilizing some of the advanced engineering tools that we use to basically develop vehicles and powertrains, looking at performance and efficiency and things like that. And also safety. We've had some discussions on safety. I'm going to hit on that a little bit and zero in on one in particular that is near and dear, or should be near and dear to most of us. Okay, hybrid vehicles are here to stay, okay, and we know that. One of the things that's interesting, just leveraging on some of the conversation we just had, go back to the 70s when we mandated higher emission standards. Well, one of the things that we had to do is we had to get away from carburetors and get to fuel injectors, right? We immediately, depending on how you want to look at it, we immediately doubled the fuel economy of the vehicle, or doubled the oil reserves of the world, however you want to look at it, because we went from a very inefficient technology to a very efficient technology. And one of the ways that was done was obviously because now we had to put in catalytic converters. We needed more precise fuel control, so it mandated the development of fuel injectors. So that technology jump, immediately we are now more emission friendly, basically more efficient with the vehicle, more efficient from an emission standpoint, et cetera. So these technology jumps we're talking about, I think we're at a point for that again, for that same sort of shift. Obviously offer better fuel economy, fewer greenhouse gas emissions, and a pathway to sustainability. I don't think there's really any real sustainable way to make gasoline. There are sustainable ways to make electricity. So it's part of the pathway. Mark talked earlier about the smart grid and things like that. It's a piece of that puzzle. Most countries have adopted stringent fuel economy and emission requirements. CAFE credits, that stands for corporate average fuel economy. Okay? That's the average fuel economy a manufacturer has to hit, otherwise they're penalized. And some of the keys to greater penetration for hybrid vehicles, there does need to be continued collaboration. Mark and I didn't collaborate on our presentations, it's just ahead of time, but I agree with them. And part of it's obviously industry, government, academia, everybody that's in this room. Government not only in regulation and incentives, but also from the research that's funded through labs like the Oregon National Lab and some of the other national labs. And manufacturers, let's face it, we love our cars. You got to continue to make appealing cars. And I put this 2000 Prius on here kind of for a reason. No, I don't think anyone in this room is going to argue that's a good-looking car, an attractive car, a stylish car. It served a purpose. It started in 1997 in Japan, came to the States in 2000. They've gone through 3 generations. In 2012, this car will have been in existence for 15 years. There's manufacturers right now that are just getting into some sort of a hybrid offering. EV offerings. This car's been around for a long time, and in a lot of ways it was part of the spark. Fuel prices, we're not going to, gasoline, diesel, you kind of see what's been happening over the last couple of years. Everybody kind of realizes this at the pump. Some, it varies regionally, but that's basically the same trend. Let me ask you a question. How many of you in the room drive a hybrid vehicle? Just maybe 15%, 20% of the room. So, the hybrid vehicles, obviously, they get better fuel economy. You're still paying the same amount at the pump, but you're hopefully filling up less, right? So depending on what you drive and how you drive, you can have considerable savings. It just makes sense. whether the gasoline was at the prices it's at right now or not. They make sense. So real quick, hybrid vehicle, by definition, there's more than one fuel source. They're typically gasoline and batteries. And one of the key enablers for a hybrid vehicle is the ability to recapture what's typically wasted energy in regenerative braking, putting that back in the battery and then drawing that energy back out to propel the car. That's really the heart of the hybrid vehicle in terms of, for example, the HEV. Oops, sorry, I'm used to this thing. The HEV, hybrid electric vehicle, the Prius, and there's, is an example. The Honda Civic is an example. There's micro, there's mild, there's strong, depending on how much hybridization is employed in the vehicle. A plug-in hybrid electric vehicle is either parallel or series, and that just relates to how is the tractive effort really connected to the engine generator or just in series with the battery. It's just, there's two different basic architectures of how you actually propel the vehicle. These are typically capable of going all electric for a certain period of time. And then there's the EV. I don't consider the EV a hybrid because it's only got one fuel source, but it is a special category. Obviously, there is no gasoline, there is no engine generator on board the vehicle. It is a pure EV. And the battery requirements vary. So there's lots of choices, cars that are out now or are coming out. Everything from, we've talked about the Leaf, we've had a lot of fair amount of discussion about the Volt. There's the Prius, the Coda vehicle, Ford Fusion, the Fisker Karma, PHEV, the Mitsubishi, the Tesla Roadster. And in a lot of ways, I give Tesla credit for, really in the last several years, really re-sparked the whole EV and made people realize that, hey, you could actually put an EV on the road and sell it. And even though it's kind of a niche car and it's very expensive, it was in a lot of ways responsible, in my opinion, for re-sparking the EV discussion recently. So what's a lithium-ion battery? Real quick, you've got an anode and you got a cathode, and you've got a separator in the middle and an electrolyte that these lithium ions, these little red balls, go back and forth between, whether you're charging or discharging. And you can think of, for example, a manganese oxide chemistry as like a parking garage. It's kind of what I call it. These lithium ions sit in there and then they migrate back and forth, and you have the same thing going on in the anode. This is really an oversimplification, but one of the things that you can do is if you can increase the amount of lithium ions that are on these that are on the surface, it's a surface area phenomenon, you can increase how much active lithium you can have on there. You can increase the efficiency of the batteries. That's one of the things that some of the folks out there are working on. So why use lithium ion? We've talked about it. It's pretty simple compared to lead acid, nickel metal hydride. It's just got better volume density and power density. So you can get a lot more out of it in a smaller volume compared to if you were trying to do the same thing on a given vehicle with these other chemistries. Now that doesn't mean nickel metal hydride doesn't have a place. For example, depending on the battery, most of the Priuses until the new one's coming out right now use nickel metal hydride. The Ford Escape hybrid uses nickel metal hydride. The CNG vehicles. So nickel metal hydride has its place, but it's being replaced by lithium ion. I'm not going to go through this. This is just kind of a list of some of the different chemistries that are out there, primarily for the cathode. But there's all kinds of choices out there. And I will say, as a company, we've used a lot of these. We've developed vehicles with probably 5 or 6 different battery companies providing lithium-ion batteries, and they all seem to have some of the same challenges. Okay, I'd say the one thing that's common amongst all these things is their drawbacks, and I'll talk about that here in a minute. So an example of a PHEV series hybrid, what do we have here? We got this big battery in the middle here that's going from 100% state of charge down to some level that we don't want to go below. It's got some amount of energy capacity at some amount of voltage when it's completely charged. And you've got this what we call a DC bus that the battery's connected here. Say it's at 400 volts nominally. And in this particular case, this would be a series hybrid. You've got an engine generator up here, which is off when you're in charge depleting mode. Charge depleting mode being you're just going to drive the thing all electrically until the battery comes down to a certain level. That power is going to go through an inverter, which is going to take that DC input, chop it, create 3-phase sine, kind of like AC power, to drive the traction motor. Whoops, sorry. The traction motor and drive the rear wheels. Then they got the hybrid control unit up here that's basically orchestrating all this. I don't show all the lines here, but it's basically in communication with all these various devices And then you have the DC-DC converter over here, which is taking the high voltage, knocking it down to low voltage for your low voltage system. So once that battery depletes, now you're down what we call in charge sustaining mode, where now you're going to just keep that battery state of charge around a certain level, say call it 20%, 15%, it varies depending on the battery. And now your engine generator is on. This generator is producing power through an inverter, also putting it on the DC bus. You can see the power's down now because your battery voltage is down, and it's all common on that bus. So you have less power at this point. But now this battery is still providing power. It's capturing regenerative braking power. It's taking some power. We typically will charge the battery slightly with gasoline, but that's a pretty inefficient way to charge your battery. You don't want to burn gasoline to charge your battery back up, but based on the vehicle requirements, we will typically put some power back into that battery by using the generator. So there's a lot of action going on here, and all this power management has got to be controlled by the hybrid control unit. And then the characteristics of that battery have to be such that it's able to handle all the rate of current in and out, this depth of discharge, the cycling over years and years, all these things going back to Mark's comment. You don't want to be walking home. This battery's got to be very reliable. And then the battery management system that's watching over this battery to make sure that the cells are balanced, to make sure the temperatures are controlled, etc. Has to be very reliable and very precise as well, so that the battery behaves and is maintained properly. So what are some of the key challenges for future vehicles from the battery? Well, they're too expensive, they're too heavy, they're too big, they don't have enough cycle life, they don't have a big enough operating window, just all those things. I will say that some of the targets, I think it was mentioned yesterday, the $750 to $850 per kilowatt hour, we've seen batteries up in the $1,000 per kilowatt hour as well, where the targets are down in this range for the DOE. So, you can have a 400, 500, 600-pound battery, and when you look at a vehicle, when you look at an EV architecture, and you look at all the components going in there, it always sticks out as the 800-pound gorilla in the room. Where are you going to fit this thing? So the technologies have to advance to decrease the size of this battery, to decrease the cost of the battery, because right now it's just not cost effective. It's highly incentivized right now. We need to have improved reliability. The thermal requirements need to be reduced, because that's just complexity and cost on the vehicle, and it's just energy wasted essentially. And then the BMS improvements, which are actually in the process of. There's a lot of companies out there working on BMS improvements. So I'll talk about this a little bit more in the next few slides. So moving to the next topic, and I'm going to go through this pretty quickly. Utilizing advanced engineering tools to achieve vehicle performance. One of the things we do as we're trying to put together a powertrain is, I talked quite a bit about the battery right there, but when you look at all the other balance of the equipment that's got to go into making a powertrain, based on the targets that you're trying to achieve, in terms of fuel economy and efficiency and top speed and acceleration and EV range and all those different things, the first thing we do is we start out with a modeling approach. And we typically use PSAT, which is now autonomy. It's actually a software that's evolved through the years, actually through some of the national labs, Oregon National Labs specifically, where you define the architecture, you define all the characteristics of the various parts that are in the vehicle. Okay, we go through. We use MATLAB Simulink, which is really a model-based development, where it's a 3D visual way to develop what the control system is going to be. It's the way engineers think. They think in pictures. Right? In the old days, we used to just type C code. We'd write a flow chart and then type in C code. Well, the MATLAB Simulink has really evolved to the point where you can generate that 3D model of your control system and then go through an auto code generation where you basically click and boom, okay, here's your C code. And then you go through software in the loop, hardware in the loop type testing, which is a verification process before you finally get to the vehicle, do vehicle testing.